Today we are going to start with the ICW3 because in the last two classes we talked about ICW1 and ICW2. Okay, and now we are going to talk about ICW3. Okay, so if you can remember or recall, we are talking about 8259 programmable interrupt controller. Okay, it has got 8 interrupt lines which are provided by the IR0 to IR7. Okay, and then we can extend the number of interrupts by cascading the cascading multiple number of 8259s, and we can reach maximum up to 64 interrupts. Okay, and we studied that the, to to work with PIC or 8259, we have to generate 4 ICWs. Okay, ICW1 to ICW4. Okay, out of which 2 ICWs are mandatory. First two ICWs are mandatory. Second two ICWs are optional. Okay, so ICW1 and 2 are mandatory. ICW2, 3 and 4 are optional. Then we talked about there are three OCWs. So OCW1, OCW3. Okay, so in total we have to work with all these control words before making it work. Okay, but remember, it is not mandatory that this is totally optional. So to make 8259 work, we have to work with, or we have to configure at least 2 ICWs, ICW1 and ICW2. And then ICW3 and 4, they are optional. They can be used if the user wants. And similarly, OCWs can be used if the user wants, or he can neglect it. The sequence of ICWs should be always like this: ICW1, and then ICW2 should follow ICW1, ICW3 should follow ICW2, and at the end ICW4. You cannot program it like, suppose you start with ICW1, it is not allowed. Okay, always start with ICW1, then ICW2, 3 and 4. You cannot change the sequence in any time. So if suppose you want to reinitialize the whole system, then again you have to start with ICW1, then ICW2, ICW3 and ICW4. You cannot change this sequence like you start with ICW4, then if you like ICW1, then ICW3. It is not allowed. Okay, you must follow this particular sequence. But in case of OCW, it is allowed. That means you can, or we can say, there is no sequence. Okay, so it is not mandatory that you start with OCW1, then OCW2, then OCW3. You can change this sequence. So you can write OCW3 first, then you can go for OCW1, and then if you want, you can go for OCW2. But remember, OCWs are non-sequential, but ICWs are sequential. And this is all the so-called small summary of 8259. Remember, this is all to handle the interrupts. And we know that when interrupts are there, when multiple interrupts are there, few things that we have to keep in mind are priority. Okay, then we have to keep, and if you talk about the priority, remember the highest priority is IR0. Okay, IR0 is having the highest priority, IR7 the least. Similarly, if we are talking about interrupts, they are totally asynchronous. They don't come according to the sequence of the clocks. They can come at any moment of the clock, be it rising edge, be it level, or be it falling edge. So when we are talking about the interrupts, then we have to keep in mind the type of triggering that they can support. So 8259 can support both edge triggering and level triggering. Okay, so all these informations regarding which device is working as a master, which is working as a slave. Slave means when you are having cascaded 8259, then only one of the 8259 will be connected to 8085. Rest of the 8259s will be connected with the um, master 8259. We can draw that after this slide. Okay, so remember all these things, that means these particular scenarios are actually configured in the ICWs and OCWs. Then only we start working with 8259. Okay, and when we say master and slave, so it will be like this. You have your 8085. 8085 is connected with 8259 8259 through pin INTR. Okay, so 8259 sends INTR towards 8085. So INTR is an input signal for 8085. In response, 8085 sends INTA. Okay, so INTA. Okay, and when any interrupt is to be generated, then remember there we need three INTAs. Okay, first INTA to generate the call, second INTA to generate the lower significant byte, then the third for higher significant byte. And if we configure that, then in that case, remember when first INTA is provided by 8085, then in such case there is, of course, there is a one data line also, data bus, which is connected between 8259 and 8085. So when first INTA is released by 8085, in such case the 8259 loads first. After the first INTA, it loads the opcode for call. So after receiving the opcode for call, 8085 understand that there must be two more INTAs to be released. So it releases the second INTA. In that case, 8259 sends the lower significant byte. Then after that, 8085 releases the third INTA, in which the 8259 releases the higher significant byte. So by reading all these three instructions or three data, 8085 understand that I have to go to the memory, which we know that it is ranging from 0000 to FFFFH. Okay, so I have to go to the memory to execute the interrupt. That means I have to go to the subroutine. So 8085 uses the same data bus, sorry, the address bus, to go to that particular address where the ISR is. Okay, then after that he executes the interrupt and then comes back. And in between that there are so many things, like 8259 can can decide how many uh, uh, how the ISRs are arranged in the memory. That means after every 4 interval or after every 8 interval. These are all provided by the ICWs. So this is the case when we have only one 8259, where you have these 8 IRs, okay, IR 0 to IR 7. But in case, suppose you have to have multiple 8259s, then in that case you will have 8259. Okay, so suppose you have multiple 8259s. So each 8259 has got its own INT line, okay, interrupt line. So that INT line is connected with the master line. So INT line of slave is connected to the IR0. Similarly, INT line of another slave is connected to IR1. Similarly, INT line of 8259 is connected to this, and similarly you can connect INT line of 8259 to IR7. It is not mandatory that in slave mode you always have to use 8259s. You can change the combination, like there are only 2 8259s, and then you can have rest of the 6 IR0s can be connected directly to the external device. So you can have a scenario like this also. It is not mandatory that you always connect all the 8259s when you are using um, master slave mode. So it is possible that you can have scenario like this also, that first two interrupt lines IR0 and IR1 are connected to slave 8259. Rest of the IR lines are connected with the device itself, suppose printer, okay, and then you can connect, suppose issue like um, mouse or something, okay, mouse or touchpad or something, a keypad or something. So in that case, now there are two 8259s and 6 peripherals. So there are 6 direct peripherals, okay, or hardware, and you have two 8259. So remember, each 8259 can provide 8 IR interrupt, okay, so 8 interrupt. So 8 plus 8, you can have 16 IRs from these two 8259s, which are the slaves, okay, and 6 from the peripheral. So in total you can have, in this scenario you can have 22 interrupts, okay. So these are all your slaves, okay, these are all your slaves. So 8259s, when we are saying slaves, so these two 8259s are your slave. Right, I should write it there, not with the printer. Printer is not the slave. Wait. Okay, so these are your slaves, okay. So this is how generally the interrupts are managed. 8259s are connected in whether in your master mode or in slave modes, okay. Now we have to know how the 8259, which is this one, is the master in this case, okay. So how the 8085 will know, which of the slave is generating an interrupt. For example, now here the challenge is, the question is, for example, here we are calling it slave number 1, and this one is your slave number 2. Now in this case you have interrupts from this slave also, okay. So interrupts from this slave IR0 to IR7, okay. So, and there may be again some other devices, peripherals connected here, peripheral 1, peripheral 2, and similarly peripheral 3, peripheral 7, Okay. In such case, if these peripherals are demanding any interrupt, how the 8085 is going to know that this particular interrupt is generated from the slave number 2's peripheral number 2? Okay, assume this particular peripheral is demanding some interrupt. In such case, how the 8085 will know that actually I have to serve this particular peripheral? Okay, this is not the question. So how rest of the lines are connected so that 8085 can know that I have to serve this particular peripheral. So now we are going to talk about how the master and slaves are actually handled, and how the devices, that means the slaves, can be identified, and how the interrupts from any particular slave can be identified. Okay, before that, we have talked about all these particular things. Okay, now for example, these ISRs, again ISR, when we are saying ISR, then in that case, in the ICW1 itself, okay, if we are using 4-bit mode, there are two different types of uh, sequencing of or arrangements of ISR in the memory. One is after every 4-byte address and or after every 8-byte address. So these informations are provided by the ICW1 itself. Okay, ICW1 has got 3 bits. Out of 3 bits, in this case we will use 2 bits in ICW1 to specify where the ISRs are located. In case of 4-bit, we will use 3 bits in the ICW1 to specify where the ISRs are. And rest of the bits, that means we need to provide 8 bits, right? So because ICWs are 8 bits. So in case of 4-byte address, we are using 3 bits in the ICW1 to specify the address. In this case, we are using 2 bits. So rest of the 6 bits are provided by the 8259 in this case, in 8 case. And in case of 4, that means if you are using 3 bits, then rest of the 5 bits are provided by the 8259. We discussed about all these things. So anyone having any doubt till this part? Because now what we are going to do is, we are going to check how the slaves are managed. Okay, how the slaves are managed and how the peripherals or the interrupts from slaves are identified by 8085 before to be served. Okay, and this is not the complete schematic. In that case, what we will need is, we will need wires or cables or buses to be connected with 8259 slaves also, so that 8085 can directly communicate with 8259. It is not necessary that the interrupt will be served via master only. That means it is not that the interrupt will be served in this fashion. That means it will always go through the master. That means the interrupt always has to be served via master. It is not necessary. It is possible that not it, it is when any slave is requesting any interrupt, then actually master is bypassed and 8085 directly serves the slave. Okay, remember, in such case, there are, when any slave is demanding interrupt, then master is bypassed. Okay, while serving, only while serving. Okay, while serving the interrupt, master is bypassed, and this is correct. Okay, this is correct, and slave is directly served by the 8085, not via master. Okay, so we are going to see how this particular arrangement is done, and how the control words can tell the 8085 which slave is actually demanding any interrupt. Okay, so this is all about a very small very small summary of the things we have talked or discussed in the last two lectures. Okay, now we are going to talk about ICW3. If you have any doubt, don't type, because most of the time I cannot read it. If you have any doubt, you can ask, okay, directly. Can we connect more than 64 interrupts? No, I told you it is not possible. Maximum, I told you many times, I told you maximum is 64, 8 into 8. Okay, you cannot go beyond that. Now that means you cannot go to 3 level or 4 levels of cascading. Only one level of cascading is allowed. You cannot go for multiple levels of cascading. Okay, now we are going to talk about ICW3. Remember, first thing, ICW3 will be needed only when we are using cascading. So why it is optional? Because cascading is optional. Okay, cascading is not mandatory. So if the user wants to design something using cascading technique, then and only then he will need this ICW3. Otherwise, ICW3 will not be needed. Okay, so the first thing that we have to remember is this particular ICW3 will be needed when you are using cascading. Okay, when you have master and slaves. And in that, there is one particular bit called SNGL, that is single, which will be equal to 0 or can be 1. Okay, and that will tell you whether there is only one master or there is master plus slaves. Okay, and remember, there is one slave register, SL register. Okay, SL register, slave register. Again, it is 8-bit register, and with this 8-bit register we can know how many slaves are there in uh, the circuit. For example, it is not mandatory, like I said, it is not mandatory that you always connect all 8 slaves. It is possible that you will connect only 1 or 2 slave, and rest of the interrupt lines, IR lines, can be free. That means something like this, where you have 8259 and you will just connect 18259 slave. Okay, this is your master 8259, and you are connecting only 18259, and rest of the interrupt lines are connected directly to peripheral, or maybe even you can leave it vacant. Okay, so it is also possible. So therefore, the slave register will tell you in which lines we have the slaves. For example, slave register is 8-bit. So if suppose 00000101, if this is the content of slave register, then it is very clear that IR0 and this IR2. Okay, these two have slaves connected in them. So IR0 is connected with a slave. We can call it slave 0. And IR2 is connected with another slave, which is slave number 2. Okay, you can call it slave number 2. Okay, so rest of the lines do not have any slaves connected to them. So this is what slave register will inform us. Okay, okay, then one more thing, 80, there are so many things that you have to remember. That's the challenge here. Anyway, 8085 can only write on this particular slave bits. Okay, slave register, it cannot read back. 8085 cannot read back the slave registers. Okay, these are the things. Anyway, you cannot remember all these things. There are so many other things also. Anyway, now the function of slave register. Now, like I said, there are two devices or two levels in which the 8259 can be connected. Either 8259 can be connected as a master, or the 8259 can be connected as a slave. So the 8259 can either work in master mode or can be in slave mode. Slave mode means those which are the slaves will be working in slave mode. The one which is working as a master, which is directly connected to 8085, will be working in master mode. How we will identify which one is working master and which one is working as a slave? If you remember, if you remember, there are two lines like SP and SP slash EN in the 8259. If you can recall, okay, wait a second. If you can recall the pin diagram, here you can see there is one line called SP, this one SPEN. Okay, so this line will tell whether the the connected device is working as a master or slave. This is one of the way by which we can identify whether the device is connected as a master or as a slave. Okay, so SP slave program. Okay, this one SP equal to slave program. When this line is zero, this line is zero, okay, then that means this IC will work as a slave. Okay, this is one of the way by which we can identify whether this particular IC is master or slave. What are the other ways? Okay, so either SP equal to 1 or, okay, remember SP equal to 0 will make it slave. Okay, so SP equal to 1 will identify that it is working as a master, or in buffered mode when M slash S in ICW4. So we are talking about ICW3, but in ICW4 there is one bit, there are two bits, M slash S. Okay, so that bit will tell you whether the device is working as a master or a slave. So either you can check the SP line, or in the ICW4 you can check M slash S line. Okay, so M slash S line means master slash slave. So if it is 1, then that means this particular device is working as a master. Then a 1 is set for each slave. Okay, leave it. Then master, okay, if the 8259 is working as a master, okay, if the 8259 is working as a master, then the master releases 1 byte of call sequence. Okay, because remember, when we have to generate an interrupt, first we have to generate a call, then we will have to pass next 2 bytes of the ISS, that means interrupt service subroutines address. So first byte will be released by the master, which will be the call sequence for the 8085. Okay, and will enable the slave to release 2 and 3 through cascade lines. Cascade lines, if you can remember, there were 3 lines in 8259, which are generally CS0, CS1, CS2. There were 3 cascade lines. Okay, so remember, when it is working in master mode, okay, so definitely with the master there will be some slaves. So if there are slaves which are asking for the interrupt, then only the master will release the call sequence. So call will be generated by the master, but rest of the 2 bytes for the ISS interrupt service subroutine will be generated by the slave through cascade lines. Okay, so cascade lines play a very important role here, because these 3 cascade lines will be connected to 8085. Okay, and we will come to see how these particular lines are connected. So remember, in master mode, the first byte is released by the master. Rest of the 2 bytes for the ISS are released by the slaves using cascade line, cascade 0, 1 and 2. In slave mode, if the device is or 8259 is slave, in that case it can be identified whether it is slave or not by either checking this particular line SP equal to 0. Okay, so we know, we just saw that there is line called SP/en. So if SP is 0, then this particular device is working as a slave. Okay, so one way to check is SP line whether it is 0, or the second option is if buff equal to 1 buffer. Okay, that is in ICW4. Okay, remember we are not talking about ICW3 now. Either SP line will be 0, or in the ICW4 we can check if buffer, this is 1 bit in ICW4, buffer is 1 and m/s is equal to 0. So if it is 0, definitely it is slave. Okay, okay, then ID2 to ID0 identify the slave. So where is this ID2 to ID0? We will check the ICW3. In that we will find where is the ID2 to ID0. That will identify the slave. Then the slave compares the cascade line, these 3 lines. Okay, the slave compares the cascade line with the lines of ID2, ID0. This will be compared with ID2 to ID0, and if they are equal, okay, if these lines are equal, that means cascades bits and the IDs which are present in ICW3, if they are equal, then byte 2 and 3 of the call sequence will be released on the data bus. So remember now, when the slaves are connected, all the data lines are directly connected to the slaves also. Okay, so we can have a scenario like this where you have the master 8259. Okay, where you have master 8259, it is connected to slave 8259. Okay, it is connected to slave 8259. I am just drawing 2. Okay, in that case all 8259 has got their own data lines. Remember, D0 to D7. So this data bus will be connected to data bus of 8085. So all of them will be connected together. Okay, all of them will be connected together. Okay, so the ISS address, the address for ISS, that is second byte and third byte, are loaded through these particular data lines only. Okay, now remember, to identify master, first check the SP line, or otherwise in the ICW4 check the m/s. Okay, so by looking at these 2 options we can identify whether the 8259 connected in the circuit is master or slave. If it is master, remember, then in that case the first call sequence will be generated by the master only, but rest of the 2 bytes will be provided by the slave. Second and third byte will be provided by the slave. Okay, through cascade lines. Similarly, in slave mode, SP will be 0, m/s will be 0 in ICW4. We will check ICW4 later. And ID2 to ID0 identify the slave number. Where ID2, ID0 are situated, they are in the ICW3. Okay, and slave compares these 2 lines, ID and CS. If they are matching, then only he will release the second and third byte of the ISS. Okay, this is the sequence. Sorry, there are so many things to remember. Anyway, let us check how the ICW 3 looks in master mode and in slave mode. Remember, A0 A0 is 1 in case of ICW3. That means if you can remember, there are two addresses in 8259. Why only two addresses? Because there is only one A0 line. So in the IC8259 there is one chip select and the other is A0. Only these two lines will identify the address of the IC plus address within the IC. So inside the IC there are only two addresses, higher port and lower port. Lower port when A0 is 0 and higher port when A0 is equal to 1. So ICW3 falls in the higher port. Okay, so because A0 is 1. So in master mode, directly all the bits from D0 to D7 will tell you which slave is connected or which of the lines are connected to the slaves. So in such case, it is directly, if it is 1, okay, if that particular bit is 1, then that means we are using the IR as a slave. Okay, so if this particular bit are 1, then that means we have slaves on that particular lines. Otherwise, if there are zeros in those particular bits, in that case they do not have any slaves, they are vacant. Okay, so first thing, in master mode, ICW3 will tell you that first thing, the ICW3 goes to the higher address, higher port. Okay, and then rest of the bits, D0 to D7, all directly tell you in which line the interrupt or the slave is connected to the interrupt. Okay, so in which line the interrupt is connected to slave. So if it is 1, there is a slave. If it is 0, there is no slave connected to 8259. In slave mode, again A0 should be 1. So that means it is high mode, high port. Rest, in the last slide we talked about ID0 to ID1. Rest of the bits will be always 0, D7 to D3. ID0 to ID2, this will be used to identify the slave's number. Okay, so these 3 bits, that means 3 bits can have 8 options. So how can we identify the slave number, which slave number is there? So looking at these 3 bits, if they are 000, then it is slave number 0. Okay, if it is 101, that is slave number 5. So looking at the D2, D1, D0, we can identify which slave number is actually requesting the interrupt. For example, 010 will be 2. 2 means second number slave. Or 101, which is 5, that means slave number 5, and so on. So to identify the slave in the slave mode, you will look into the 3 bits D2, D1, D0. So ICW3 can be of 2 types. One is when the IC is working in master mode. The second is when the IC is working in slave mode. In slave mode, we will look into the 3 bits D2, D1, D0 to identify the numbers of the slave. Slave number 0, slave number 2 up to slave number 7. In master mode, directly we will read S0 to S7, which is D0 to D7. Okay, and if it is 1, then that means there is a slave connected. If it is 0, there is no slave connected. So in this way, ICW can have 2 different versions for 2 different modes, for master or slave. Now coming to ICW4. If you can recall, the first thing that we can see here, which is red, if you can recall, in ICW4 will be needed only when we pass the requirement in ICW1. ICW4 will not be generated if we do not specify that in ICW1. Why? Let us check. Okay, if you can recall ICW1 here, this is the ICW1's format. You can see the D0 bit. In the ICW1 itself, we specify the D0 should be 1 or 0. If it is 0, that means ICW4 is not needed. If it is 1, only then ICW4 will be needed and we will pass the ICW4. Only if D0th bit of ICW1 is 1. Otherwise, we will not pass ICW4. Okay. So, if suppose ICW4 is needed, then when ICW4 will be needed, and why the user will use ICW4? So, ICW4 is needed only for following conditions. One, if you are using 8086. First thing, if you are using 8086 with the 8259, then ICW4 will be needed. Okay. Second option, if 8259 has to be configured into some special modes like fully nested mode, buffered mode, automatic end of interrupt mode, and all that. We will come to these modes, what are fully nested mode, buffered mode, or automatic end of interrupt mode at the end of this particular topic. Okay. Only if you need to configure the 8259 in particular special modes, okay, special modes, then in that case only you will need ICW4. Remember, ICW4 is needed only when 8086 is connected with the 8259, or when you need special modes, not the normal modes, special modes like fully nested mode, buffer mode, automatic end of interrupt mode, extra. Okay. Okay. And definitely ICW1 will inform the system that whether ICW4 is needed or not. Now, so what is the ICW4's control word? A0 is 1 again. So that means it is again for higher port. Okay, higher port of 8259. So this will go to the higher port of 8259. First 3 bits will be 0. So this identifies that we are passing ICW4. Okay. So what is the identification of ICW4? D7, D6, D5 will be always 0. Okay. Rest of the bits, the first bit D4 is SFNM. That means whether you want special fully nested mode or not. Okay. Nested mode, if you can remember what is nesting. Nesting means calling an interrupt through another interrupt. Okay. Or we can say nested loops we have made. So calling another loop, one loop from another loop. Okay. So for example, for I equal to something, and then you specify for j equal to something. So there are 2 loops, one loop inside another loop. So that is nested looping. Similarly, you can have nested interrupts also, where one interrupt is called from within another interrupt. So that means when one interrupt is being served, at that time, suppose another interrupt comes, then how the system will be managed. So that is called nested interrupts. Interrupt inside an interrupt. Okay. So do we need nested interrupts? If we need, we will keep it 1. Otherwise, we will keep it 0. Fully nested mode. Okay. Otherwise, we will not use this particular. Now there are 2 bits which are used generally together. Okay. One is buff and other is M/S. In the last slide, we talked about this particular bit, whether it is master or slave. Master mode or slave mode. In which mode is the device connected? We can identify either from SP line or from this particular bit also. And buffer. So these two, when used together, 0x. That means if this particular bit is 0, okay, then it does not matter what is this bit. Okay, so in that case non-buffered mode will be used. Second, if this particular bit is 1 and second bit D2 is 0, then it is slave or master mode, buffered slave or master mode. Okay, so buffered mode will be there, and in that you will be using the device in slave mode. Okay, we discussed that if it is 0, if this bit is 0, then it is slave. Okay, we can have bar here. Okay, so if it is 0, then it is slave. If it is 1, we are using it as a master mode. But remember, if it is 1, then buffered master. If it is, this is 1 0, or it can be 1 1. So 1 means buffered. Okay, and here also 1 is buffered. Buffered is okay. Plus 0 specifies that the device is slave. 1 specifies the device is master. Okay, then D1 will tell you whether the interrupt is automatic end of interrupt kind of thing, or it is normal end of interrupt. Automatic end of interrupt and end of interrupt, these are two different uh, we can say special modes. Okay, so we will come to these modes at the last slides. Okay, so these modes, or end of interrupt and automatic end of interrupt, this can be decided by D1. That means when any interrupt is complete, when any interrupt is being served by 8085 and the service is completed, then definitely we have to inform, or the 8085 will be informing the 8259 that look, I have completed your interrupt related task. And what is the procedure to inform that we have finished or we have ended the interrupt or the task is completed? For that, we will generate one signal, and that can be of two types: automatic end of interrupt or normal end of interrupt mode. These are two different modes in which, by which you can inform that interrupt is completed. If it is 1, end of interrupt is auto. If it is 0, it is not auto, it is normal end of interrupt. D0 of IC4 will tell you whether you are using 8086 or 8085. Okay, if it is 1, we are using 8086. If it is 0, we are using 8085. So in ICW4, first 3 bits D7 to D5 will be informing that it is ICW4. Why? Because the first 3 bits will be always 0. Fully nested or not, buffered or not, master or slave, automatic and end of interrupt or not, microprocessor is 8086 or 8085. This is the information that we can collect from ICW4. Okay. Now, this is I have discussed this things. Okay, let me check if there is any extra information here. F equal to 1, special nested mode. Okay, if buff equal to 1, it is buffered, and sp/n will become our master slash slave. Okay. Okay, if m is equal to 1, then that means the 8259 is programmed as a master. If m/s is 0, then 8259 is programmed as slave. Okay, then AEOI, that means automatic end of interrupt. It is in that mode or not. We will check what is this particular mode. And last, whether the microprocessor connected is 8086 or 8085. So if it is 1, this particular last bit D0, then we are using 8086, and if it is 0, it is, sorry, yeah, if it is 0, then 8085. Now, after this is all about initialization. When before starting the interrupt service, we have to go through all this ICW1 to ICW4 and only after that we can start sending the interrupts. If you can recall the flow chart. Okay, so first we will pass the ICW1 and then we will pass the ICW2. Okay, it is mandatory. So in ICW1 there are some informations like the triggering level, type of triggering, the the address is 4 byte or 8 byte or so on, and then ICW2 will provide you the higher address byte. There is no confusion in that. So ICW1, ICW2 is mandatory, so we have to pass these two. Then after that we will check whether we need cascading or not. If it is needed, then we will use ICW3, otherwise no. Okay, if this is needed, then only we will use ICW3. Otherwise we can escape ICW3 and directly go to the ICW4. Again it will be checked whether ICW4 is needed or not. ICW4 is needed or not is mentioned in ICW1 itself. The D0 bit of ICW1 will tell whether ICW4 is needed or not. If needed, we will pass it. Otherwise, we will bypass or we can escape that ICW4 also. And then only we are, or the system is ready to accept interrupts. So we have gone through the initialization process and now the system is ready to accept interrupts. Okay, so that means now the vehicle is ready to start. So you check the, if you take the same analogy, you check the gear, status of gear, you check the brake, you check uh, the lights are on or off, and then everything you checked before starting the vehicle. Now the question is, now you can start the vehicle. Okay, so this is ready to accept interrupts. After that, now the question is, when you are driving the vehicle, what are the things that you have to keep when you are using that vehicle? So these are initialization processes complete. Now we are going to check what are OCWs, operational control words. That means when you are using the device, then what are the things that you have to keep in mind? Okay, so operational command words. So remember there are three operational command words. After this, okay. Okay, leave it. Now let us talk about the first operational command word, OCW1. OCW1 directly tells you which of the interrupts are being masked. Okay, so OCW1 can be used to set or clear, that means to allow or to mask, okay, the interrupts directly. So by OCW, while the interrupt is being served, you can mask or unmask any particular interrupt line. Okay, remember there is one interrupt mask register in 8259. Okay, if you recall the block diagram, there was interrupts ISR, interrupt service register, and IRR, interrupt request register. Then you have in between priority, okay, priority checker kind of thing, and then you have here in the bottom you have the IMR, interrupt mask register. So this, in this register you will have the information about which of the interrupts are being masked. Okay, for that, to mask any particular interrupt or to unmask any particular interrupt, we can use OCW1. So OCW1 can be used to mask or unmask any particular interrupt in IMR register. Okay, so there will be M0 to M7, we can say mask 0 to mask 7. Okay, and if it is 1, then that particular line is masked. Masked means it will not be allowed to generate any interrupt. Masking means stopping. Okay, so if that particular bit is 1, then that means that particular line cannot generate any interrupt. Let us check what does that mean. For example, now remember, this particular OCW is again high port address. Okay, it is passed to high address because A0 is 0. This is very important, and uh, when before programming, the user must know that out of these ICW1, 2, 3, okay, so and 4. So ICW1, 2, 3, 4, and then OCW1, 2, 3. How many of these are belonging to higher port, and which of these ICWs actually belong to lower port? Similarly, which of these OCWs belong to higher port and which of the OCWs belong to lower port? For that, you can check A0. First, we should know whether the ICW1 or ICW or OCW belongs to higher port or lower port. Okay, that is one of the most vital information that the designer should know. Now, OCW1, remember, this is higher order or high port command. Okay, so this will go to the high port of the 8259. Now, coming to the rest of the bits, D0 to D7. D0 to D7 means in that we can mask or unmask. If it is one, mask set, that means deactivate the interrupt. Interrupt will not be allowed from that particular line or particular bit. For example, if this is, okay, we will come to the example. And if it is 0, wait a second. If it is 0, if it is 0, then it is unmasked. That means interrupts are allowed from that particular line. It is taking time to save. Okay. For example, assume IR4 and IRC request should not cause any interrupt to the processor. You remember that 8259 has got IR interrupt request 0 to IR 7 interrupt request 7. If we want to block interrupts through line 4 and 6, if we want to block line 4 and line 6, we don't want to allow any interrupts through these particular lines. In that case, we'll be providing the OCW1 with a command, this command. Now you can check, this is 0, 1, 2, 3, 4, this is masked, 5, 6, this is also masked. So that means there cannot be any interrupt generated from IR4 and IR6. They are masked. Now what we are doing, this thing we can read 50H. Okay, this is 50H. So to pass OCW1, remember, assume here, because this address, how we came to this address, because this address is generated via chip select, combination of chip select and A0. So this is higher address, so higher port address. Okay, so definitely lower port address will be 50. So this particular OCW1 should go to the higher port. So therefore 51. This 51 is generated by the combination of CS chip select and A0. Okay. So don't worry about this particular address, why it is 51. It is assumed that particular chip select is having that circuitry which makes it to look like 51. Okay. Now, So we can mask or unmask the, so simply ICW1 to mask or unmask any particular interrupt. Now coming to OCW2, from here the things get a bit more complicated. Okay, so better I jump to the next slide itself, because here we can discuss OCW2 through the word itself rather than through these lines. Okay, okay, this is what the OCW control word looks like. It is A0. A0 is 0, that means OCW2 should be passed to lower address. Okay, it is not passed to the higher address. Then D7, D6, D5. Okay, these three bits actually controls the modes, like like the modes of rotation should be needed or not. We will come to that, what is rotation mode. Then the modes end of interrupt, and SL I am not recalling, some level. I will, if there is information of SL level. Okay, slave level or something. Okay, now how to identify OCW2? In OCW2, D4 and D3 will be always 0. Okay, this is important. Now then D2, D1, D0 will be used to identify the level of the interrupt. Okay, we will come to that in the next slide itself. Okay, so this is the structure of OCW2. Remember, D4 and D3 will be always 0 in OCW2. Okay, now the combination of these three bits are SL and EOI can push the device in all these modes of working. So you don't need to remember it. Okay, but just for your information, that these three bits are used to drive the IC into different modes. What are the different modes available in the 8259? There are 8 different modes allowed, and those 8 different modes can be configured using D7, D6, D5. Remember, 8259 can work in 8 different modes. Okay, and which mode is being in which mode that particular 8259 is working, for that in the OCW2 we can configure D6, D5, D6, D6, sorry, D7, D6, D5, these three bits, and we can drive that particular IC into that particular mode. Okay, so what are the different modes? You don't have to remember, but just for information, EOI end of interrupt mode, rotate in automatic, end of interrupt mode clear. Just a second. Okay, so sorry here. Okay, so we can have rotation mode, which kind of rotation we want, which kind of end of interrupt we want, which kind of priority should be provided to that particular mode. So these kind of things can be set using these three bits. Okay, so don't have to by heart it. It will take hell lot of time to by heart these things. All these things cannot be by hearted. Rather, when you are working with the IC, you take the data sheet, and if you want to drive that IC into that particular mode, you will come to that OCW and check what we should put into that. Okay, then only you can work. Okay, so SL means no specific level. I think it is specific, a special level. I have to check specific level. Okay, SL. So L tells you the level of interrupt. For example, 000 IR0 level 0. Okay, and IR1 now 001. Okay, you can check it like this: L2, L1, L0. Okay, so if it is 000, you are talking about IR0. Okay, 001, that means IR1, and then you can go up to IR7. So level of interrupt can be decoded by these 3 bits. Okay, and in which mode they are working you can identify with the 3 bits D7, D6, D5. So OCW in short tells you the mode in which the IC is working. Mode, okay, if you are using any mode, so in that case, in which mode that particular IC is working, and which of the interrupts are working in that particular mode. Okay, like whether IR0 is working in that mode, IR1 is working in that mode, or any IR5 is working in that mode or not. Okay, so for that we can use OCW2 for 2 informations. One is the mode in which the IC is working. There are 8 different modes. Okay, and second is the level, that means the interrupt which is working in that particular mode. How to identify whether it is OCW2? In OCW2, D4 and D3 will be always 0. Okay, and that will tell you we are passing OCW. Remember, now here OCW2 is lower address. This is low address or lower address byte. Okay, so lower port. Now coming to OCW3, which is the last. Okay, in OCW3, first thing that you have to know is it is again low port control word. Okay, so if you want to pass this control word, you have to pass it into the lower port of the 8259. Okay, first thing. Second thing, that ESSM, enable special mask mode if it is needed. I don't think these kind of things are needed when you are programming. It is very highly in depth. Okay, it is not needed. You cannot remember all these things. Impossible. One cannot remember these things. Okay, we can talk about it, but to by heart or remember all these things is very difficult. Anyway, ESMM, enable special mask mode. Okay, this is one of the mode. If you want to enable that, you can enable that through D6. Okay, when this bit is 1, it enables special mask bit to set or reset special mask mode. So there is one special mask bit in the 8259. You can set or reset it by using ESMM. Okay, so when ESMM is 0, then special mask bit becomes a don't care. So that means leave it. Oh, no issues. Special mask mode if SM is 1 and SM. That means remember, if these 2 bits are 1 and 1, then and only then you enter to special mask mode. Okay, otherwise you will not enter into special mask mode. So both the bits, if the ESMM and SMM are 1, then 8259 will enter into special mask mode. We will check what is special mask mode. I think I have the details of masking modes and all. Okay, let me check. If it is 1 and 0, or rather I should have made a table. Okay, if it is 1 0, 8259 will revert to normal mask mode. So special mask mode only when both these 2 bits are high. If this particular bit is 0, 1, 0, then we are talking about normal, or the 8259 goes into normal masking mode. Okay, done. If ESM is 0, SM has do not. So if this is 0, ESSM is ESMM is 0, then SMM don't gets into don't care condition. That means it does not matter whether it is 1 or 0, we will not be changing the mode of the masking. Okay, rest of the 3 bits. So here this P, RR and RIS actually are used to control rotation, special level, specific level, and end of interrupt. Leave it. These things are not important. It is not. It is too. We are getting into too deep. Okay. OCW3, D7, D4, D3 will be in this sequence always. Okay. D7 will be 0, D4 will be 0, D3 will be 1. This is the identification of OCW3. In OCW3, these 3 bits will be always in the same sequence 0, 0, 1. That is D7, D4, D3 will be always 0, 0, 1. Now, okay, the same special mask mode. ESMM, if it is 0, okay, this is representing this particular graph. Okay, this particular line. So if ESMM is 0, then there can be 2 options, 0 and 1. Okay, so does not matter, because this particular bit becomes don't care which bit, SMMM. So it does not matter if it is 0, as ESMM is 0, then this particular, it can be 0 or 1, does not matter. Okay, so nothing will change, no action will be taken. So ESM, this is okay, I have talked it. If it is 1 and 0, we will enter into, this means normal mode. Okay, normal mode. If it is 1 and 1, then we are going into special mask mode. Okay, this is done. Next, this is getting too depth. Okay, P is representing whether you are using polling mode or not. Okay, leave it. Then the combination of these 2 bits, RR and RIS. Okay, read register and IS, read interrupt service. So I don't think you can remember all these ICWs and OCWs. No, not necessary. Anyway, again, if RR is 0, then this is don't care, does not have any effect. Okay, if RR is 1, okay, if RR is 1 and this is also 1, in that case we will check the read interrupt service register on the next read. Okay, read pulse. Leave it. It is too depth. Cannot remember these things. Okay. So in summary, we are going to check what are the things the 8259 can do. So first thing that we have to remember is we have to pass the ICWs to initialize the working. Okay, so before starting the 8259 working, we have to initialize the command words ICWs. Okay, so after passing all the required ICWs, we can start writing the, or we can start receiving the interrupts from the 8259. Okay, then we have to go through the OCWs if required. These are not mandatory, these are optional. So With the OCWs, we checked that OCWs are generally used when we have to change the mode of working or to change different levels of interrupts and all, masking the interrupt, unmasking the interrupt and all. So basically there are four modes in which we will be mostly interested. One is fully nested mode, second is rotating priority mode. Then rotating priority mode, priority mode means we can even change the priority of any particular. For example, we said that IR0 to IR7. Okay, so this is the highest priority and this is the lowest priority by default. Okay, so definitely if suppose okay, IR0 is served, then definitely the next interrupt that can be served is IR1. So this is the first interrupt to be served and this is the second interrupt to be served. So basically we are kind of rotating this one, then this one and this one, and so that means it is going like this. And after IR7 you can again go for IR0. This is rotating priority mode. Okay, so after serving the present priority, the priority will be highest priority will be to the next one. We will check that all those things. Okay, then special mask mode, that means how we can mask different interrupts. Polling mode, so we will be checking all these four modes, what are the the work, how the 8259 works in these particular modes and when the user can use these particular modes. So remember, OCWs are controlling the modes and the masking of the thing. Okay, remember one more thing, OCWs can be initialized anytime or it can be called at any time after the initialization. That means after once ICW is passed, completed, and the 8259 is started working, you can call OCW at any time. And I told you OCW do not need any sequence. You can call OCW2 first, then you may call OCW1, or then you may call OCW3 also. So it is your choice. There is no need to have any sequence. Okay, so no sequencing is needed. And how the 808 the IC actually understands whether OCW1, 2 or 3 is coming, some of the bits are always either 0 or 1 in the OCWs. Okay, for example, this OCW3, D7, D4, D3 will be always 0, 0, 1. In case of OCW2, D4, D3 will be 0, 0. So in this way, and OCW1, there is no such restriction. It can directly use all the bits to mask. Okay, so OCW2, D3, D4 will tell you OCW2 is there, and OCW3, D3, D4, D7 will tell you that this is OCW3. Okay, now first mode, which is fully nested mode. So we know what is nesting. Nesting means calling one function from within that particular function. Okay, so that means one interrupt from another interrupt or one loop from another loop. This is called nesting. Okay, in this mode all the interrupt requests are arranged from highest to lowest. Okay, first thing that you should remember is all the interrupts are arranged from highest to lowest. So highest is IR0 and lowest is IR7. So first it is arranged in that way. Any interrupt can be assigned highest priority in this mode. So it is not mandatory that IR0 will be the highest after that. When you enter into the fully nested mode, you can give the highest priority to any particular interrupt that you like. Okay, and the priority sequence will then begin at that IR only. So that means first you will arrange them. Okay, let us see how we arrange them. So it is like this. By default, IR0 is the highest priority. Then 1, 2, 3, 4, 5, 6, 7, which is the lowest priority. This is by default. Okay. But in fully nested mode, you can change that priority level also. So now here you have specified that IR4 is the highest priority. So automatically the next one will become the lower priority. So highest, then 1, 2, 3, okay, then 4, 5, 6 and 7th priority. So IR3 became the lowest priority automatically. Okay, so in this mode, remember, you can change the priority of any particular interrupt. Okay, first thing, and then automatically the next one will become lower than that, and automatically when you come back to the same, the the bit just before the highest priority will become the lowest priority. Okay, you can select your own priority. So any interrupt request can be assigned highest priority in this mode, and automatically the priority just before that will become the lowest priority. Automatic rotation mode, I am not going into deep. Okay, these things again can be specified and used in OCWs and ICWs. We are not going into that depth. Okay, automatic rotation mode, in this mode a device being served receives the automatically lowest priority. Okay, so if suppose IR4 is being served, then automatically that particular interrupt will become the lowest priority. Okay, so automatic rotation mode. So here you can see, before, assume IR4 was the highest priority, so definitely IR3 will be the lowest priority. Now after serving IR4, automatically after serving IR4, IR4 will become the lowest priority. And who will become the next highest priority? The bit which was next to IR4, that is IR5 will become the highest priority. So automatic rotation mode, that means whichever is served automatically becomes the lowest. So the next one becomes the highest. So in this way, the priority is rotating. If you check, the highest priority rotates from one level to another level, and then it comes like this, and then it goes like this. Okay, so this is automatically rotating. Automatically the highest priority becomes, after serving the highest priority, it becomes the lowest priority. Okay, specific rotation mode. So in this mode it is similar to the automatic, except that user can select any IR for the lowest priority. Okay, here whichever you have served is becoming the lowest, but in specific rotation you can specifically say that I want this to be the lowest. Okay, so specific rotation means that user will tell which one is going to be the lowest priority, and automatically the next will become the highest. Okay, but automatic means the 8259 will manage the priority levels and rotate the priority from highest to lowest. So highest means which one is served becomes automatically lowest in auto rotation mode. In specific rotation mode, the user can specify which interrupt request should be given the lowest priority. So specific is, you can say, manual. Okay, or manually you can control. This is automatically fully though. So 8259 has got the authority to change this. Now specific rotation. Okay, example, if suppose IR5 is programmed as the bottom of the priority device, IR6 will have the highest one. It is clear. So the the highest priority will be just after that. If IR5 is the lowest, then the next bit will be always the highest. So IR6 will be the highest. Okay. And remember, OCW2 was used to specify, okay, to set the level of this particular modes, or to set the priority of these modes. Okay. Leave it. Poll command. Poll mode interrupt output function is. These are very complicated. Okay. This is clear. Poll command can be passed in the OCW3 when P is equal to 1. That was in the control word itself. So 8259 treats the next RD read pulse. Okay, read pulse to 8259. No, these are very complicated things. Okay. End of interrupt command. This is important. Okay. So after serving the interrupt, definitely we have, or the 8088259 has to release end of interrupt command. And end of interrupt command can be of two types. One is automatic and end of that is AEOI, that is automatic end of interrupt, or you can have end of interrupt command, normal end of interrupt. So after completing the interrupt service, corresponding ISR bit needs to be reset to update the information of ISR. Because remember, when 8259 is serving any interrupt, okay, suppose any interrupt came, IR. So 8085, it is serving this 8259's interrupt, okay, assume. In that case, any other interrupt should not come first thing, okay, or otherwise if it is coming, then 8085 has to manage the previous interrupt and the next interrupt also, depending on the priority. So after serving the interrupt, 8085 has to inform 8259 that I have completed the interrupt. So after completing any interrupt service or any ISR, when it is complete, the ISR bit needs to be reset. That means because it was set, okay, it was set, so it need to be reset. After that, after completing the interrupt, it has to be reset, and that is done by your EOI. Okay, so non-specific EOI, in that we do not specify that we have to end the interrupt from this particular line. You just pass it EOI, whichever interrupt was there, it will be automatically reset. So non-specific EOI, when this command is sent to 8259, it reset the highest priority ISR bit automatically. That means whichever is being served is the highest right now. So non-specific, you do not specify that go and reset the interrupt of that particular line. Whichever line is the highest priority interrupt at that time will be reset by using non-specific EOI command. Specific EOI, this command specifies which ISR bit to be reset. In that case, we will tell that okay, IR7 has to be reset or IR6 has to be reset. Okay, in this we pass the particular ISR to be reset. Here we do not pass any specific ISR, rather whichever is the highest ISR, it will be reset. Here no, we will tell that particular ISR has to be reset. Automatic end of interrupt. Okay, so if we are using the device in automatic end of interrupt mode, then no command is necessary. You don't have to pass these two commands, end of interrupt or specific or non-specific end of interrupt. If it is in automatic end of interrupt, you don't have to, that means 8085 do not have to send any end of interrupt command. It will be automatically done. How? During the third INTA. Okay, during the third INTA, first INTA for call, second INTA for the lower byte of the ISS, that means interrupt service subroutine, and third INTA for the higher address of the or higher byte of the interrupt service subroutine. So just after the third INTA, ISR bit will be reset. So just after acknowledging the third interrupt, automatically ISR bit will be reset using, if you are putting the device into automatic end of interrupt mode. Okay. Thus, any IR can interrupt the service routine irrespective of its interrupt priority, and interrupt enable flip-flop is set. So in short, you can remember, if you are using automatic end of interrupt, then 8085 don't have to pass specifically end of interrupt command. After the third INTA, automatically whichever interrupt bit was requesting the interrupt will be reset. Simply after third INTA, automatically that particular ISR will be reset. So these are the three ways by which 8085 informs 8259 that your interrupt has been served, or your interrupt service routine has been served or completed. Okay, now what will happen if suppose there is an interrupt coming in between the interrupt acknowledgement? Okay, so now this is the question. Like suppose 8259, okay, was getting an interrupt. Oh, the time is over. Okay, this is the last slide, I believe. So if suppose IR2 is being served, okay, and suddenly, okay, IR0 comes. So at time t equal to 0, IR2 requested the interrupt, but at time t equal to 1, IR0 came, and suppose this interrupt will take time from t0 to t3. Okay, so at t1 IR0 came, which is of higher priority. Now what the 8259 will do, or how the interrupt will be managed, because now in between the lower priority to be fully served, the higher priority interrupt came. In such case, okay, if any higher priority interrupt comes between two INTA pulses, that means this particular interrupt has not been started being serving. It will be served only when you will get all the three INTAs. So before getting the third INTA, suppose a higher priority interrupt comes, then in that case the INT line goes inactive immediately after the second INTA, because third INTA was not passed. Okay, so before third INTA, the interrupt line will go inactive. It will not be served. Okay, interrupt will not be served. After an unspecified amount of time, there is no specific time. Okay, INT line is activated again to signify higher priority interrupt is waiting for service. So that means IR2 will not be served. Rather, for some time period, this INT line will become deactivated. Okay, deactivated for unknown time period. After that particular time, INT line will be all again activated. Okay, it will be activated, and that signifies that actually a higher priority line is waiting for another interrupt. So 8085, okay, 8085 first sent INTA 1, and then it sent INTA 2. Before INTA 3, IR0 came. So what the 8085, how the 8085 will know that there is another interrupt? So this line will automatically be deactivated. That means there is no sense of these previous two INTAs. Now after some time, again the new INT will be generated, which will tell the 8085, look, previously there was an interrupt which actually was a lower priority. Now there is an interrupt which is of higher priority. So definitely you need to pass new 3 INTAs. Okay, so thus inactive time is not specified and carry between these two parts. Okay, designers should be aware of this consideration, and okay, leave it. So now when the interrupt line is active again, the 8085 has to pass new 3 INTAs after the line is getting activated. Okay. Other features of it to find an interrupt trigger, interrupt status. Okay. Okay, this was talked about before, that we can pass either edge triggered interrupts or level triggered interrupts. This is one of the feature, and we can check the status of particular interrupt, whether it is being served or not, and so on. We can check the status by reading the status information can be used. Okay. Polling method 8 to 5 can be set up, double T yoga, can be set up to function in a polled environment. Okay, leave it. Done. Okay. We can mask the interrupts using IMR. These are all we have discussed about these things. Each bits in the IMR can be set or reset to tell which of the lines are being masked or unmasked and